Good morning, everyone. Thank you for braving it in the heat. Let's get started. So today's lecture 4, today's our last lecture on kind of this broad overview of the internet. And just a quick recap of where we were. We were in our top-down approach to understanding how the internet works. We said there were 3 major tasks: defining the problem, which we said was very simply to transfer data from one end host to another, and then decompose or break down the tasks that you need to implement in order to get the internet working. And we had walked through that, and what we had arrived at was a breakdown of tasks that looked like this, where we said we have 5 layers. At the very top, we have applications. That's the application layer. That's built on top of having reliable data delivery. So we're not talking about packets yet. That builds on top of this global best effort packet delivery. So we've moved to packets, and we've moved to best effort, which in turn builds on top of our best effort local packet delivery, which builds on top of just physically moving bits, putting bits on a wire. Okay. Before moving on, I wanted to spend a little bit of time expanding on this distinction between global and local packet delivery, because the last time around I think I saw a few confused faces, and it can be tricky to get in the first pass through this. And so here's what I mean by this distinction between local versus global delivery. So let's say we started with a picture very much like the ones we've been looking at throughout, where I have end hosts connected by switches. In practice, you'd be using different link technologies to build those links and switches. So for example, in this particular network, there's a portion of the network that is made up of Ethernet links. Ethernet is a particular link technology. I'm sure you've heard the term before. But then you might have a portion, for example, when you're going across a long distance, you might have a portion that's built out of some kind of optical technology. So OTN, or optical transport network, is one such technology. You're not expected to know the details of what OTN is, or at this point even what Ethernet is. Just think of it as it's a particular type of link technology. And then as you go further in the network, you might have more Ethernet links, and you might have some cellular links and a cellular network at the edge. And so when I think about going through from one host to the other, each one of these link level technologies quite often has its own way of doing addressing and routing, or having a path through just that portion of the network that is made up of that link technology. Okay? So here in this example, you could see you could have a path going from that host there that is going through the Ethernet portion of the network. Then there's a separate portion that's going through the optical portion of the network. And then down there again, I have a different Ethernet network. Okay? So in each of these portions of the network, I have a link technology specific way of getting a packet or getting data from one point to the other. Okay? That's what I mean by best effort local packet delivery. That Ethernet network at the top has no idea how to get a packet all the way through to the destination, but it knows how to get a packet across a series of Ethernet links. It only speaks Ethernet. It doesn't understand how to speak the optical technology. Okay? But that is best effort local packet delivery across a particular packet using some link technology specific way of getting across that network. Okay? And if you remember the very first lecture, we said the internet interconnects networks. That's what we mean. It's going to interconnect that Ethernet portion, the optical portion, and again that last Ethernet portion. But each individually only knows how to Ethernet only knows how to go across an Ethernet network. Optical only knows how to go across an optical network. So we need another level that can take that ability to deliver packets across an Ethernet network and the ability to deliver packets across the optical network, and then again the ability to deliver packets across the Ethernet network. We need another layer of functionality that's going to be able to take those capabilities and stitch them together into an end-to-end path. And that is what the network layer does. That's this global end-to-end packet delivery that IP implements. And it implements it by using what each of these link-level technology networks give you. And that's a large part of the power of IP is it doesn't reinvent the wheel. It doesn't say I'm going to redo link technology and every single network. It knows how to stitch them together. Okay, I haven't told you how it's going to stitch them together, so you don't have to know it at this point. But that's the breakdown of tasks. Okay? So that's how we came at this particular layering architecture. Does that make sense? Any questions before I move on? So moving on, so what we've done is we've broken down this end-to-end task that the internet has, which we start with applications talking to applications, all the way down to bits on the wire. The next step we have to consider is how are we going to actually tie those pieces together, and how are we going to make all these layers work end-to-end. And for that, I want to take you back to this example we had in the last lecture where we said, we had this analogy of CEOs want to talk to each other, and the way they talk to each other is by going through these layers that now I hope you can relate to internet layers. But that at each layer, we said that peers understand the same things. So CEOs understand what CEOs say, the aide understands what the other aide says, and FedEx delivery people, the delivery infrastructure, they know how to speak to each other. It's going to be very much the same with our internet layers. So peers at the same layer are going to be able to understand each other. And the way they're going to be able to understand each other is because we're going to define a protocol. And if you go back again to our first lecture, we talked about what a protocol is. But so the communication between peer layers on different systems is defined by these protocols. And a protocol, going back to lecture 1, is simply a specification or an agreement between two entities on how they communicate. It's kind of like speaking the same language. Right? But more formally, it means that there's a syntax for communication. That syntax tells you this is in those headers exactly what fields you should expect for that protocol. Right? So for example, you'd say, I have 64 bytes header, the first 32 bits tell me what the destination address is, and so on. So you're going to specify exactly what the format of that header is. And we're also going to define the semantics, which is when you receive this packet, here are the steps you expect it to take. So every protocol definition is going to come with this syntax and these semantics. There are lots of protocols. As you've seen, we have lots of layers, so it's reasonable to expect at least one protocol at each layer. In practice, there are far more, and we'll get into that in a minute. What you should know is that protocols exist at multiple layers. Some of them are actually implemented in hardware. Some of them are completely in software. There's a wide variety of them. They tend to be defined and standardized by some standard body, some international standard body. The most common one that you'll see is the IETF, which is the Internet Engineering Task Force. So it's a body made up of representatives from companies, from research, from pretty much it's open to anyone who wants to participate. And in those committees, they define these protocol standards. Okay. So here's just one snapshot of protocols you can expect to see at different layers. Right. Some of these should look familiar to you. HTTP is a level 7 protocol. Ethernet, what we just talked about, is a layer 1, layer 2 protocol. The network we've talked about, IP, TCP, UDP, are layer 4 protocols. There are a few things to observe here. One is that you can have different protocols at the same layer. Okay, this might seem surprising to you. All it means is that you have a different implementation of the task that had to be implemented at that layer. And if you think about it, it makes sense. You'd have an Ethernet protocol at layer 2 because you want to know how to speak over Ethernet links. But you also want to speak over optical links, so you have an OTN protocol that knows how to speak over optical links. At layer 7, if I look, you have HTTP as a protocol that we use for web transfers. It's used on the web. But we also have a protocol NTP that's used for network time synchronization between two entities over a network. That's the network time protocol. But it's still an application level protocol. Similarly, if I look at layer 4, the transport layer, TCP, which I'm sure many of you have heard of, what it does is it'll take data from the application, turn it into packets, and implement reliability. Make sure that all of those packets are reliably delivered between the two end hosts. UDP is another transport layer protocol that does the same thing in terms of taking data and converting it into packets, but it doesn't worry about reliability. So it provides no reliability guarantees. So if you're looking at this and you're thinking, but we said that protocols work because you have to speak the same language, we do still have to enforce that. So I cannot, for example, have an Ethernet sender talking to an OTN receiver. That's not going to work. I can't have an HTTP client talking to an NTP server. That's also not going to work. The other thing you might wonder about then is, if you look at this diagram, I told you one layer will use the functionality provided by the lower layer. But now if I have multiple possible implementations of the lower layer, what am I talking to? And that's a choice that at every layer you will make. So for example, HTTP chooses to build on top of TCP typically. So that'll be a particular implementation. TCP builds on top of IP. IP might have to build on top of Ethernet so it can talk to an Ethernet network, and at the same time know how to talk to an OTN implementation so that it can also connect to an optical network. So there's no inconsistency with having multiple protocol implementations at the same layer. And typically you'll hear the term network stack. You can think of, it's kind of an informal term, but you hear it all the time. It's an instantiation of this protocol stack. It's an implementation based on implementing a particular protocol at every level in the stack. And it's a stack because we're combining those implementations into a path by which network traffic is going to be processed. Okay. There is one crucial thing though in this picture, which is we only have one IP protocol. So at the network layer, there is only one protocol. It's IP. That's the glue that stitches together all of these other networks and all of the applications on top. Okay. Any questions? Yeah? Yeah. Any others? And again, these are all examples. I'm not expecting you to know the details of any of these. Some of them we'll dig into, but others we won't. Yeah? Sorry? Yes, great question. So IP version 4 and version 6, both are different versions of the same IP protocol. But again, IPv4 will talk to IPv4 and IPv6 will talk to IPv6. I'll get back to that in just a second. Any other questions? Okay, so recap, 3 important properties you should remember of layering. Each layer depends on the layer below. What that means is it uses the interface or the functionality provided by the layer below. And at the same time, it implements an interface or functionality that is useful to the layer above. It only interacts with the layer above and the layer below. So that's strict layering. And you can have multiple versions in a layer. We talked about that at length, but only one IP protocol. That's the only protocol at the network layer. So why is layering important? What do you think? We said it's a form of modularity. It's a particular form of modularity. Why is this a good form of modularity? Yep? You can abstract away the details of everything other than the layer underneath you, pretty much. Why is that good? Why is this kind of strict separation of concerns useful? You know it. This is every time you write code. Right. So it's key. What this enables is innovation, basically. That innovation that can proceed mostly in parallel. If you're at the application layer, for example, and somebody changes their network from optical generation 1 to satellite generation 2, you don't need to care. Imagine if you had to re-implement your browser or re-implement Skype or whatever your favorite application every time somebody changed a link on the internet. It would be a complete disaster. But instead, with this kind of strict layering, you can have innovation that proceeds almost independently in individual layers. And this is doubly crucial because the internet is a vast system, right, implemented by a huge variety of vendors and players. And so this allows very different communities to pursue innovation independently. The physicists who are figuring out how to build better links don't have to worry about security issues in your browser or any of the concerns that application developers might worry about. And we see that because that's exactly what has led to innovation at, I would say, most levels in that layered architecture. We all know and enjoy a large number of applications. There's also a large variety of link technologies. Right? These days we have satellite that's coming up, we have millimeter wave, we have all kinds of technologies that just didn't exist 40 years ago when we built the internet. The one layer that I would say is the exception to this is, as you might suspect, given we have only one, it's the IP layer, that network protocol layer. And evolution of the IP layer has been painful over the years. So even going from IPv4 to IPv6 has been a 20-year process. And we'll talk about IPv6 a little later in the semester, but it's not a terribly ambitious protocol. It was not a huge change over IPv4. And even then, it's taken many, many decades to actually roll it out. Questions? Okay, So now, all we've done so far is decompose the problem. We haven't said exactly who's implementing what and how. Okay, so we're going to get to that next. And here the question is really distributing layers across the network. If all we were doing was taking those layers and running it in your laptop or somebody's server, that we wouldn't worry so much about exactly how we're assigning tasks or who's running what layer. The real challenge in the internet comes because we have to partition that functionality between the end hosts and the network. And that partitioning is really going to determine what the network implements, what is the job of the network. Okay? And so that's what we're going to do next. Let's first think about the end host. Okay? And I want you to tell me, what do you think, which layers get implemented at the end host? And now, remember the layers, the two ends of it, you have the application, and then the very lowest layer is just the ability to put bits on a wire. So which of these functions do you think the end host has to implement? Yep. The application, for sure. What else? Does the end host have to be able to put bits on the wire? You're nodding your heads? Yes. Right? If I stick an Ethernet cable into my laptop, I expect my laptop to be able to actually send data over that Ethernet link, which means it must know how to put bits on the wire. And so bits arrive on the wire at your laptop or at your phone, which means you have to implement L1. And we also know we're running applications at the end host, so we know we're running L7. We have a strictly layered architecture. This means you have to implement all layers at the end host, all the way from picking bits up off the wire to handing it to an application. So all layers run at the end host. What about when we think about the network? Right? If I walk through that reasoning again, I would say, okay, bits come in on the wire, I have to implement L1. I have to be able to move packets from one switch to another across links, so I have to implement L2. And I have to do end-to-end delivery. That is exactly what the network's job was. So I have to do L3 as well. And we're going to talk about this at length, but the network does not implement layer 4 and layer 7. So it doesn't, crucially, no one expects the network to run applications. That was never really on the table. But the important thing here is that the network does not implement reliability or reliable data transport. And this is actually not what the first iteration of the internet did. So this was an important change when they changed from ARPANET, which was the government's first attempt, to what is today the internet. And so this gives us a very simple diagram that looks like this at the highest level, where the end host, you see all 5 layers, and a switch or router is implementing L1 to L3. Okay. I'm going to dig in on both the end host and the network view a little bit more closely now. Let's start with the end host. Right, so we said the end host, think of this as your laptop or server, implements all 5 layers. What does that actually mean? Let's open up that end host. If you look inside your laptop or your machine, to first order, what you have is your network interface card. Okay? This is where you go stick your cable in, or your wire in, or your radio lives. And then you have things that come in on that network interface card get handed to your operating system. And in particular, the networking stack within your operating system. What I mean by this are the portions of your operating system that handle processing traffic between applications and the network interface card. Okay? Because your operating system does a lot of things. So the networking stack is the relevant portion for us of the operating system. And then it also hands, hands packets up to the application. So we have these 3 major components within your end host. Should not be too surprising when you think of which layers get implemented where. We're going to put the application layers going to run at the applications, and the physical and data link layer are going to run on your network interface card. This is really the job of putting bits out onto the wire or packets out onto the wire. Where do you think your network and your transport layer should be implemented? It's pretty obvious. Yep. In the operating system. Any guesses on why? And we're now actually, I should say, in the realm of not you have to do it this way. We're more in the space of this is how common practice. Most systems you go look at, this is how they're built. Why would you put the network and transport port layer into the operating system?
You want the operating system to be able to think about making decisions in terms of should I send these packets or how do I structure
that's reasonable. So you want to look, can I say you want to manage across applications. So you have all this traffic that different applications want to send out, and you want to be able to maybe do something intelligent with that, prioritizing one application over another, or making sure one application is not hogging all the traffic or the bandwidth. Sure. Anything else? Yep. Right. So that's, the primary driver, which is, this is a pretty general task. Imagine if every application you wrote, every time you had to write an application, you had to worry about how do I take this file or this key value store or this recording, and I have to chunk it up into packets. And then I have to worry about how to make sure that every packet gets delivered to the end host. I have to implement reliability. It would just be a lot of work for every application to redo it. You could, nothing stops you, but it's much more convenient to have that functionality in your operating system. To implement it once in a general fashion, and it's a general service that all applications can use. And in some sense, this is the role of the operating system, is to have services and abstractions that are useful for applications built on top of it. So that's why we have typically the network and the transport layer implemented in the OS. It's not the only way to do things. You can certainly find systems out there that either put this functionality at the application layer, or even increasingly these days, for example, in data centers, that push that functionality down into your network interface card. And the reason they do that is simply to shrink the footprint, to not consume CPU resources on doing network and transport layer processing. Any questions on the end host? Right. There is another trick that you have to think about when you're looking at the end host. So let me ask you to think now about, that a packet is arriving at this end host. Okay. And we said the packet contains the destination address. This is the address, the unique address of this host on the internet. Okay. This is what allowed the packet to make its way across the internet and reach this end host. Now the packet arrives at the network interface card. Let's say the network interface card does something like it raises an interrupt. The operating system then sucks the packet up into the OS from the NIC. And now the packet is sitting at the operating system. When this packet arrives, how does the operating system know which application it should hand this packet to? Yep. Right, exactly. So there should be some information in the header that allows the OS to know which application this packet has to go to. In everything we've talked about, so I haven't told you about this piece of information so far. Right? So you didn't actually have enough information to know how this packet makes it to the application. So now what we're going to do is introduce this concept of a port, that in the header there's going to be a port number that identifies which application you have to send, the OS has to send the packet to. In particular, that port identifies the attachment between an application and the operating system. So this can be pretty confusing, so let me clarify one thing. In networking, we have two different types of ports, and it doesn't help when students are trying to not be confused. So we have two different types of ports. One is physical ports. If I take a switch, or if you take your laptop, you have the physical port where you connect a link to that device. Okay? That's the ports I think many of us are familiar with. But there is also a logical port. The operating system supports this concept of a logical port that is very different, has nothing to do with the physical port on the switches. The analogy is that this is where the application connects to your operating system. And that's why we call it a port. But it's an entirely logical entity. Okay, so physical port, the thing on your device where you go plug in a cable. Logical port, where your application plugs in or connects to the operating system. And so in your next section, you're going to talk about something called sockets and how this relates to ports. Sockets is the operating system abstraction, or API, that allows an application to connect, or an application process to connect to the networking stack or your operating system. So you'll study this interface in depth, but the way this works is that when an application wants to connect or wants to access the network, it's going to open a socket. Okay? That's the abstraction the OS provides. The OS is going to associate that socket with a unique port number. Okay? Not the physical port number. This is the logical port number. And so now when port numbers get carried in packets, and so when a packet arrives at the OS, it says, this is the port number. It looks it up to see what socket is associated. It hands the packet to that socket, which is a way of handing it to the application. Okay? And you're going to see sockets in the socket interface in much more detail. What I do want to focus on in this lecture, however, is the implications for the packet header. So far, we've said that a packet has to contain the destination address. Right? This is the information the network needed to get that packet to your end host. Now I'm telling you that packet should also contain a destination port. And this is used internally within your end system by the OS to know which application to hand the packet to. Any questions? Yeah?
When we're talking about applications, we're talking about one browser, not individual websites within that browser?
Right. It's a process. So from the point of view of the OS, it doesn't actually care what application is running in that process. It's a process. It just knows which process to hand it to.
Different websites have different ports?
Typically, if you had a different, you would be writing different server applications for different websites to serve different applications, and then they would bind to different ports. But you could also build it either way. So I think we went over this. When a packet arrives at the end host, it's delivered to the socket, which is the process associated with that packet's destination port. So really what we've created here is a role for the operating system where it acts as an intermediary between the applications and the network interface card. Okay? So the application has a very clear task. It thinks about data. It thinks about those key value stores, about files, about images. Right? That's what the application is concerned with. On the other hand, the network interface card, or the driver is the code that runs on or interacts with the network interface card hardware, has a very clear task. It has to think about packets and the link technology it's sending those packets over. The OS, or the network stack within the operating system, is what mediates between those two, what converts between those two. It takes that data and converts it into packets that the NIC can send out. That's the role of your OS and the network stack within your OS. It's a very important role. So I'm going to recap. At the end host, we have L7, typically part of your app, L3 and L4, typically part of the OS, and L1, L2, typically implemented in your network interface card. Any questions before I move on to the network? Yeah? Right. That's a great question, and I believe you cover that in section again. But typically, the way this will work is that the server side, remember, server listens for connections from clients. So a server will connect on a well-known port. Port 80 is probably the port you've heard about. A client can locally then pick any port it wants, connect to that well-known port, so that's how it knows which port to send a message to on the server. The server, when it receives the message from the client, knows what port it sent it on. So you just have to flip it around, and you know how to get back to your client. So moving on to the network side of things now. So again, recall we said we have this picture, all 5 layers at the end host, only layer 1 to layer 3 in the network. And we said layers on either side interact with the peers corresponding layer. They run the same protocol. We're going to dig down into that a little bit more now. Just to make this picture more useful and interesting, I'm going to add an additional router. So you can see that that interaction is not just between end hosts and routers, it's also between 2 routers. Okay. And I'm going to start looking at what protocols we're running at each of these layers now. Okay, so a very simple protocol diagram would say, these are examples. Again, these are not the only protocols you could be running. These are very typical protocols that we run. So at the application layer, we could be exchanging HTTP messages. Again, I'm not telling you at this point how that message is actually flowing through the network. I'm just telling you what message or what protocol both sides understand. So what does it mean now that we've talked about protocols and where things run? What this means is that the HTTP protocol implementation, that code, is running at layer 7 at the 2 end hosts. At the applications, you're running code that implements the HTTP protocol. What that means is it knows how to create HTTP messages with the right format, knows how to receive an HTTP message and parse it correctly, and so on. Beneath that, we have TCP byte streams. Don't worry about what the term byte streams means. It's just, we'll get to it much later in the semester. It's just how TCP, the terminology we use for how TCP thinks of data. Okay. So a TCP byte stream, again, this means you have the TCP implementation that's running in your OS at both end hosts are exchanging TCP byte streams. When we get to IP, we have this IP, the code that understands how to process IP packets, running both at the end host in your OS and in the switches and routers. So now when we talk about peers that speak the same language, notice it's going not just between the end hosts, but also in the switches. And the same with Ethernet until finally, and then the same with Ethernet. And then below that, we're going to actually put bits out on the wire. Again, so far I'm talking about logical communication, what both sides understand. What would you do if I said that actually that link was a transport, optical transport link? So it's an optical link, OTN. What would you change in this picture in terms of what protocols are running well? Yep. You're right. You wouldn't have to change anything at the IP layer or the TCP layer or the HTTP layer. What about at the Ethernet layer between those two routers? So I told you Ethernet, I can't have an Ethernet sender talking to an OTN receiver, and Ethernet doesn't understand OTN. What would I do? Yep. Yep. Exactly. So the routers would implement both. And this is where it starts to be crucial that you can have multiple data protocol implementations at the same layer running together on the same device even. Right. So here you would be running the OTN protocol implementation at those two routers. And those are the implementations that would put packets out onto that optical link. You would also be running the Ethernet protocol because they have to know how to speak to the Ethernet links that are used to connect to the two end hosts. So we're running both protocol implementations. Any questions? Yep. Within a router, yes. If you had a router, and not all routers do this, but certain routers at borders will do this, where they speak they have a particular type of interface on one side and a particular type on the other side, yeah. Yeah, hold on to that question. We're going to get to it. I haven't told you exactly how a message flows through this yet. I've just told you what the two peers at a particular layer have to understand, not how to make that work. So just to get to exactly that question, and this should become clearer, but I'll stop again and ask you if it is clearer. I want to recap how we talked about physical communication. So far what we've talked about is logical communication, right? Peers are exchanging messages that both sides understand. I haven't told you how those messages actually get there. That's the actual physical path that a message is going to take. So we're going to do that now. I wanted to bring you back to that analogy we had again with the CEO and the two CEOs talking, where we said you start with this letter travels down the layers, so kind of down the stack, then across the world, and then back up the stack. Okay, that was the path of the letter. And so we'd said that communication goes down to the physical network, that was the FedEx infrastructure in that example, and then goes back up to the relevant layer. So now, looking at that in the context of our layers, what that means is that this red line here is the physical path the message is going to take. It's going to start at the application on one side, go down the stack, get out onto the wire, go to that router, go back up to the IP layer, again down, go out the next wire, up, down, next wire, and then up the end host. I'm now going to make this a little bit more complicated, but now you'll hopefully start to understand exactly how a message flows. Let's try to blow that up a little bit more. So far we've been talking about that logical communication between peers. What does that mean? So here I'm going to start using these dashed lines to represent logical communication and solid lines to represent physical communication. Right. So we said we have these HTTP protocol implementations running at both end hosts. Right. So you have some application level message to send. We also said HTTP builds on top of the TCP implementation or the layer 4 implementation at that system, right? So the HTTP code up there It's going to have a message. It's going to hand it to the TCP code. Just pass the message down or invoke the interface of the TCP code at that end host to the left. Okay. Same thing, passing it down to IP. Right. That IP logically is speaking to the IP layer in the other routers and switches. But physically, what that IP layer is going to do is it's going to send the message down to the data link layer implementation. In our case, that's Ethernet. That's running at that end host. Okay? And then that Ethernet interface actually finally is the thing that puts bits out onto the wire. So path of a message through this diagram looks like this. Where I started at the application level, I kept passing the message down the stack, then the message was transmitted over a wire, and then it went back up the stack. The important thing to notice here is what's going on in this router, right? Where the message came in on the Ethernet interface. Remember I told you Ethernet does not know how to talk to OTN, and it doesn't have to with the way we've wired these modules, right? Ethernet just passes the packet up to IP. And then what does that IP module do? It'll do something like it'll look at the destination address and say, if you remember that forwarding table, it'll say, my next hop in this path is to go out over this OTN wire. And that's why it hands it down to the OTN interface at the data link layer. Okay, so there's no violation of layering here. We don't have two protocols that don't understand each other speaking to each other. Does that make sense? Yeah? Right, so the HTTP message that's at the end host to the left is effectively sending an HTTP message to that message to the HTTP implementation on the right, the end host. At the end of the day, that's what we're trying to achieve. But in order to get there, it's not like HTTP doesn't have a wire to HTTP. It has to go over that physical network at some point. And the way it's going to do this is by passing it down these layers. And I'm going to get to this in a bit, but each layer is going to add some information that helps the next layer down forward that packet on. Yep? The OTN interface in this example is required because I have an OTN link between those two routers. Thanks for raising that. I should have made that clear. The only reason I need that OTN interface at the data link layer there is because I have an OTN link. If I had a wireless link, I would have needed the Wi-Fi protocol implementation. Right? Yep.
You're using the same framework in the routers too. You still need to go to the IP layer and come back to the transporting layer.
Right. So the question here is, why did I have to go up to the IP layer? And thank you. That's the crucial part in this picture, so it's good to get it right. The reason I had to go up to the IP layer is, think about it, what if I did not have the IP layer? Right. And I wanted to send the message directly from Ethernet to OTN. In order to make that work, Ethernet would have to know what format or what interface OTN supports. And so every link technology in the world would have to know how to convert between all possible link technologies. Ethernet would have to know how to send a message to OTN. OTN would have to know how to receive a message from Ethernet, and so on. Instead of which, what we're saying is the only thing that you need to know how to, if you're link technology, if you're Ethernet or OTN, the only thing you have to know how to do is hand a packet up to the IP layer and accept a packet from IP. As long as we all know how to interface to IP, this can work. Yeah. That's a great. What if that middle link was Ethernet? Then you wouldn't have to go through IP. That's absolutely correct, because you understand what's on the other end. You had a follow-up question? Or say the same question. Okay. Other question? Yep. Locally, as in to a host, what would local? Two end hosts connected to the same router. Again, it depends on what the interface at the other end host was. So if I got rid of the second router, but I said the link between it, the first router and the last host was OTN, I would still need to do the conversion. If it was Ethernet, I wouldn't have to go up to the IP layer. Yeah. You could have. So the question is, why is it an OTN interface? Could it have been an Ethernet interface? Typically, different links have different characteristics. So for example, a Wi-Fi link is much lower bandwidth. An OTN link can be 100 terabits per second. So the assumption in this example is the operator had a reason for putting a high bandwidth, low delay optical link in there. So that's kind of an assumption going into this picture. Yeah. Yes. So the question again is, if that middle link was not an OTN link, was an Ethernet link, would I have needed to go up to IP? The answer is no, because Ethernet would have known how to pass it between Ethernet. And I'm going to get to that explicitly in a few slides. But, yeah. Right. So this is jumping ahead to many lectures, which is how would Ethernet have done it? So within a link technology, Ethernet has its own addressing scheme and runs its own routing protocol. And so when you received the packet, you would have said, what is the Ethernet destination, and do I know how to forward it? Right. But in this case, there was no Ethernet destination. You had reached the destination. You were done with Ethernet, so you hand it up to IP. If that didn't make complete sense, this should make sense when we talk about Ethernet later. Yep. Yeah. Right. So from the point of view of this Ethernet interface here, you received a packet, you're done. And when you're done, what do? You take out the Ethernet header, which we're going to the next slides now, and you send it up the stack, which in this case is IP. So in the very first lecture, we said that the job of the internet is to interconnect networks, right? That it's a network of networks. This implementation here is exactly what makes that work. The fact that you have IP there, if you look at the role of what IP is doing in this picture, it's interconnecting different link or different network technologies. And as long as we speak IP, then we know how to jump between this Ethernet and OTN network. There's more. I haven't told you how IP has the information needed to know that it had to go out over that OTN interface. That's going to be the job of routing, but that is exactly the role that IP is playing. Right. So to recap physical communication, are we all good with that previous picture? Yeah? Okay. So to recap physical communication, we said communication goes down to the physical layer, across a network, and then up to the relevant layer. Okay, so I've just told you what that physical path is. I haven't told you how each layer knows what to do with the message and where to send it next. In going back to our CEO context, the way each layer knew what to do with the message was through this notion of taking a letter, putting it in an envelope, putting it in a FedEx envelope. And every layer knew how to take something from a layer above it and then how to put it in a format or in a package such that the next layer knew what to do with it. And similarly, on the receiving side, like the aide knew that when you get the FedEx envelope, you open it up, and you take the envelope, you open it up, and you take the letter to the CEO. Right? So each layer knows how to kind of unpack packaging and repack the message. And we said, so communication goes down to the physical layer network, then up the layers, and at each level we add some packaging. And the lowest layer, so that truck carrying the FedEx envelope, has the most packaging. Right? And the application has the least packaging. It has the original message. We're going to do the same thing on the internet. So at layer 7, the host, you take that application data, and remember layer 7 we said was going to, for example, be implementing HTTP. So you will add a layer 7 header to that application data. You'll add an HTTP header. This is what allows the HTTP peer on the other side to understand what that message is. You'll then hand it down to your layer 4 implementation, or TCP. TCP is going to put its own TCP header on top in addition to that HTTP header. and then pass it down to the IP layer, or L3, which is going to put an IP header on top. Okay, and down to the L1, L2, which is your data link layer, and getting the bits out on the wire. And then when you send this message along the way across to the other end, L1, L2 is going to look only at the data link layer header, knows what to do with it. It's going to then take it off, send it up to the IP layer. IP layer is going to look at the IP header, send it up to TCP, and so on up till you get to the application layer. Okay? So that header is what allows these peer implementations to talk to each other. And if you look at each of these layers, it's only looking at the header that's relevant to itself. So the data link layer never looks at the HTTP header, for example. The IP layer is not looking at the HTTP header. It's only looking at the information in that IP header. We haven't yet talked about what goes into those headers. That's what we'll be doing over the semester. So packets contain multiple headers. If you actually went and looked at a packet on the wire, it would have all of those headers stacked one on top of the other. Is that making sense? Yep. Mm-hmm. Yeah, so I don't have, just to not make this diagram even more complicated, I don't have the router here. What the router would do is exactly the same as the end host. When it receives the full packet, it would, the Ethernet, going back to our previous example, the Ethernet implementation would look at the Ethernet header, and then it would say, okay, I'm done. This was the Ethernet destination. So it takes off the Ethernet header, hands it to the IP layer. The IP layer would do what we've talked about in previous lectures. It would look at the destination IP address, that's the address of the end host, would look it up in a table to know which interface to send it back on, and then send the message back down to the optical implementation. Okay? It would never look beyond the IP layer header. So it never looks at a TCP or an HTTP header. Got it? Any other questions? So here's an exercise, and you'll be doing this in the discussion section as well, is take the previous slide where we were adding and removing headers, and think about this physical path through this complicated protocol diagram. And ask yourself at different points in this path, what headers do you expect to see on the packet? It's a great exercise by which to make sure you're following all this. So for example, if I told you the IP implementation at this first router, what headers are on the packet and what header is that module looking at? The answer in this particular case would be that the packet at that point has no L2 header, has no data link header. It does have an L3, L4, and L7 header. So it'll have an IP, TCP, and HTTP header. But it's only going to look at the IP header, the L3 header. Yep. Yes. They would be routing on different headers. This is a subtlety that I think will be clearer when we get to Ethernet. The Ethernet, if I had two Ethernet, and I actually have this example right here, if I had two Ethernet switches side by side, they would be looking at Ethernet addresses and deciding to go out to the next interface. They would not be looking at IP addresses. Right. Yep. It depends at which layer. At this point in the router, yes, it would have all the headers. You would take off the Ethernet header. So if we go back to here, if you look on the receiving side, as you move up the stack, you're taking off headers. Yeah. So at this point, you would have the Ethernet header. You would take it off. At this point, there's no Ethernet header. When you send it back here, this interface adds a sonnet. Oh, I have sonnet here. Sorry, that's the precursor to OTN. A sonnet header. Yep. No. Right. So if these were both Ethernet, so let me go. I have these slides to explain a historical side note, and then I'll come back to your question, which is, we've said switches and routers are the same. Don't worry about it. Historically, the reason we had those different terms was that you could buy Ethernet switches, and Ethernet is the most common type of switch that we see in most deployments. You could buy an Ethernet switch that actually did not implement the IP header, the IP layer. It was just able to switch Ethernet packets. It has its own protocol by which you learn about paths through an Ethernet network, and it does this routing on Ethernet headers. And so we would call these switches, and the ones that actually implemented IP we would call routers. We don't follow this distinction anymore because at this point you can go look at any Ethernet switch that's sold on the market. They also implement IP. Okay. So, yep.
Does IP have access to transfer header and chooses not to access it, or does it not?
It has access. If it wanted, those bits are there in the message it received. It's just as per the protocol, it should not be looking at the TCP header. There are violations of this in practice, but the protocol, IP protocol, does not require you to look at the TCP header. Yep. It doesn't. It can only get you across an Ethernet network. The minute you try to leave the Ethernet network, it doesn't know what to do. Then you need IP. Within one Ethernet network, which is defined as a set of interconnected Ethernet links, you would run an Ethernet routing protocol, a spanning tree or some more modern form of Ethernet routing, which we haven't covered yet, so you don't have to know. So I'm going to continue in this class to use switch and router interchangeably. Just wanted you to know where that distinction comes in. So review, we're kind of done with our top-down view of how the internet works. As you can tell, this concept of layering and adding headers and so on can get pretty tricky, so make sure you understood it. We have these 5 layers. All 5 of them are implemented at end hosts, and only 3 of them are implemented in the network. Before I move on, any last questions on that? Yep. This is a question, does every header have the same size? No, not necessarily. It depends on how that protocol is defined. So IP, for example, has something called IP options that could make the header be different in length. But you have to know how to, as an IP implementation, you have to know how to figure out what the length of your header is. Any other questions? Okay. Let me take a 2-minute break, and then we'll continue on with the question I want you to think about is, why is this particular assignment of tasks good? And so we've said this is the breakdown into layers, and we've said typically the end hosts implement all 5 layers, the network only 3. We're going to take a more philosophical look at this now to talk about why that particular partitioning has been very useful on the internet. Okay, let's continue, and I'm going to try and do a speed end-to-end principle in 20 minutes. So let's try to make this work. So the question of why is this assignment a good one? And a lot of what we're going to be talking from here on, the kinds of lessons and terminology we use, comes from someone called Dave Clark. He was the chief protocol architect for the internet back in the 80s. So back in the 80s, there was this committee called the IAB, the Internet Architecture Board. they were not a standards body, but they were there to offer architectural guidance to the people developing protocols like TCP and IP and so on. And Dave Clark was the chief protocol architect there. So he's not the person that invented TCP, IP, BGP, but he's very much the person that gave us the language and the rationale for why the internet works this way. And so there are two papers in particular that are classics. When you take a PhD level class on networking, these are the first two papers, every class I know of, these are the first two papers that you'll go read. They're both beautiful papers. They're actually very accessible. If you want to go peek at them, there's a link at the bottom. The second paper, which is the design philosophy of the internet protocols, is the paper we're going to be reading later in this semester. Okay, so I'm going to cover kind of the argument that is in his first paper, the end-to-end arguments paper. I'm going to do a first pass through trying to explain what the end-to-end argument is. We're going to come back to it much later in the semester because I find when you've actually understood routing and TCP in more depth, then you better appreciate what Dave Clark is trying to say. So we're going to do a first pass now and an in-depth view of the end-to-end principle later. So what does the end-to-end principle mean? It's a guideline. It's not a rule. You don't have to follow the end-to-end principle. But it's a guideline that guides the debate about what functionality gets implemented where in any distributed system. So it's actually a fairly general rule or general guideline for how you should be partitioning and assigning tasks to different pieces in a distributed system. In this class in particular, we are going to be thinking or using it or thinking about the functionality that a network should implement. What does the end-to-end principle tell us about what the network should or should not implement? Even one step more specific, we're going to be thinking in this lecture about should the network implement reliability? Okay. Should it be the job of the network to worry about reliability? So before I even go there, what does it mean, or what do I mean when I say that the network should implement reliability? You could implement reliability in a number of different ways. I'm going to give you one just so you have a mental picture. The idea is that the network is going to do a little extra work to make sure that the packets it's trying to send are getting to where it's trying to send them. It's not just going to send it out and hope it gets there. So for example, typically what this would mean is something like router 1 will send the packet to router 2, and then it'll wait for an acknowledgement to come back from router 2 saying, I got this packet, you can now send me the next packet. And it'll not just be I got this packet, it's actually going to send something like a checksum. Is everyone comfortable with the idea of a checksum? Yeah. So it's kind of like a hash or a fingerprint that says this is the actual content I received. So it's going to send that checksum back to 1. And so then 1 can say, will know that yes, 2 received the packet, yes, it received the correct packet, and yes, I can now send the next packet. This is actually what the first iteration of the ARPANET, which was the first iteration of the internet, implemented. And you're going to do this repeatedly at every link. So this would be one example of a network that's trying to implement reliability. If it did not get that ACK back, it would resend the first packet. And maybe it would resend it 5 times or so. And just to set the stage, there is nothing we can do to guarantee 100% reliability in all cases. Right? If I have heaven forbid, a nuclear attack that takes out half the internet, I'm just not, there's no path between A and B, I'm just never going to be able to send a packet to B. Or if B crashes, I'm not going to be able to get the packet to B. So we're not talking about 100% in all possible cases reliability. We're talking about things the network can do to increase the chance that your data will get there correctly. Okay, and so the question we have at hand for the next 20 minutes or so is, what do you think? Should the network implement reliability? Is it a good idea or not? And to frame that thought, here's an example that Dave Clark uses, which actually came out of there when they were building these systems, which is, let's say that the task I have at hand is to do a pretty good, reliable transfer of a file from host A to host B. Okay. The steps this is going to take is, the application at host A is going to read this file from the disk, from the local disk at that machine. It's then going to send it to the operating system, which is going to then send it out over the network to the other end host, which is going to send it up to the application, and then at host B, you're going to write that file to your local disk. Okay? So we're taking a very end-to-end view here. Right? It's not just the network. We're taking the end-to-end view of what is this application trying to achieve? It's actually trying to move a file from stable storage, the disk on one host, to the machine, the host, the storage, the disk on the other host. Okay. That's kind of the end-to-end view of what we're trying to do. And what do we want to achieve? As I said, we can't guarantee that the file will get there, but if the file gets, we would like the file to get there with a pretty high chance, a good probability of getting there. And importantly, we want to make sure that if the file reaches, that it's a correct file. It's not corrupted, it hasn't lost some bits, and so on. If host B believes it has the file, it should be the correct file. And so you could imagine two proposals for how to solve this. Right? One is implement reliability at every step. So make each of those 5 steps we've talked about reliable, okay, individually. And then we've stitched together these reliable steps to have end-to-end reliability. That's one proposal. If this is the path we go down, we're going to be saying the network should implement reliability, because we want a pretty good chance that the network is getting packets through, and that it's getting them through without them being corrupted. A second proposal I'm going to put on the table is we don't do any of the things in step 1. Instead, what we're going to do is have an end-to-end check, and if the check fails, host A retries. What does that end-to-end check look like? And again, end-to-end, right? So I'm not just thinking about the network. So if I want to implement solution 2, what I'm going to do is that the application at host B, after it has written the data to disk, is going to reread the data, compute a checksum. So again, a summary of the contents of that packet, of that file. Send that checksum back to host A. Host A is again going to read the file, make sure that the checksums match. And if the checksums match, it's going to say, okay, you have the right file, you can go ahead and use it. Back to host B. So I want you to think now about which would you do, and think about it a little bit in 2 dimensions. Let's think about it first in 1 dimension, which is correctness. If I was concerned about correctly getting the file across to host B, which of these solutions do you think I would want? And to kind of refine that question a little bit, if I had solution 1, do I need solution 2? Or if I had solution 2, do I need solution 1? Does solution 1 work? Does solution 2 work? Thoughts? Which would you do? Yep. So the point is, what if the suggestion is, what if the checksum, the transfer of checksum failed? So I dropped the message that said, here's my checksum. What would happen in that case? So host B would not be able to use the file, right? Is that okay? We said, we're not guaranteeing delivery. In fact, neither of these solutions can always guarantee delivery in the worst case. So let's think about solution. Is solution 1 clear first? What we're trying to do, right? We have these 5 steps, and we're going to try and make each step reliable. Any questions on what solution 1 and solution 2 are doing? Okay. So I'm going to assume, so let's go look at correctness. I'm going to assume everyone's clear on what these 2 solutions are doing. The problem is, solution 1, you cannot make it perfectly reliable. What if, for example, I actually, in this case, the application at host B, after it received the file, but before it wrote it to disk, it crashed. Right? Then host B, you wouldn't have received the file. That's one possibility. A worse one, let's say you had a component that had a bug. Right? Let's say you misconfigured your network, or you misconfigured the application, so it actually doesn't run the checksum calculation. And so you sent a corrupt file, and host B accepted it because of a bug, did not actually check the contents of the file, and so you had the wrong file. In solution 1, what you would have is actually that host B would accept a buggy file, a corrupted file. Right? So even though I got the bits across, I got the wrong bits across. And so unless you could make every single component guarantee that it is correct, that it's implemented correctly, and that it has no bugs, and that it doesn't fail, unless you guarantee those things, you actually cannot guarantee the correctness of the file transfer. And so in order to guarantee the correctness of the file transfer, you're going to end up doing the end-to-end check in any case. Because that's the only way to actually make sure that the file that reached at host B is the same as the file that was at host A. So you're going to have to do that check in any case, or if you don't do it, the endpoint could be in an incorrect state. What I mean by this is that host B has accepted a file that is actually a corrupted file. Does that make sense as an argument? Okay, solution 2 can also fail, right? So what if, host B sent the checksum to A checked it and said it's all good, and then it said, okay, you can go ahead and use it. And then that you can go ahead and use it message got dropped. Then host B is not going to be able to use the file. So you can still fail with solution 2. You can always create a scenario where either of these solutions fail. But there's no scenario in which solution 2 will allow host B to have the incorrect file. Because the only way host B will use the file is after it gets a message from host A saying, yes, you have the correct file. You're okay. You're good to go. So you can have host B in a state where it doesn't have a file, or it doesn't have a file it's allowed to use, but you cannot have host B in a scenario where it has the wrong file and it goes ahead and uses the wrong file. Does that make sense? Right. Any questions on this line of argument? Yep. The end-to-end check that we're adding at the end is sent separately after you've finished the transfer. So I'm not sure I followed did I get your question, guy? Okay. So what's the impact of failures here? And I mean failures not just in the sense of I dropped a packet, but I actually gobbled the bits, I corrupted the packet. If in solution 1, if you had a network failure or bug, it actually led to incorrect behavior at the endpoints. It led to the wrong set of bits being transferred to B. And so if you want to trust solution 1, you have to trust host A has to believe that host B is correctly implemented and the network is correctly implemented. This is a huge assumption. Right? We never want to assume that other components are bug-free, especially application code. Very unlikely that you can always assume it's bug-free. In solution 2, the endpoint semantics, however, are decoupled from the network failure. The network can still fail. It can still corrupt bits. But when it does that, it doesn't lead to incorrect behavior at the application layer. Instead, the host A is only relying on the fact that it has a correct implementation. It is possible that host A has a buggy implementation and it got the wrong checksum and it accepted it. But you brought on your own failure in some sense, or you relied only on your own implementation being correct. Okay, so the intuition for what Dave Clark, building on that example, his argument for why the network should not implement reliability, is that there are certain application requirements, like correctness, reliable transfer, correctly transferring the bits in a file, for example, or security is another one, and I'll get to that in a minute. But there are certain functions that you can only correctly implement them if you take an end-to-end view, if you implement them end-to-end. That was the final checksum that we're calculating on that file. And so in those cases, what we should think about is the end system, if the end system must implement that functionality for correctness. So in this case, the end system was doing that end-to-end check and retransmission. It was going to retry. If the end system has to do that in any case, because it's the only way to ensure correctness, and if in implementing it you achieve reliability, then his argument is we should not implement those functions in the network because it's unnecessary and it adds complexity to the network. So this was the argument for why one should not require the network to implement reliability. We can take it out of the network. Does that make sense? Any questions on this? Yep. Yes, let me rephrase that question. It's a good one. So the scenario is, what if the checksum that B had sent back to A was actually an incorrect checksum? And the network happened to corrupt this bit such that that incorrect checksum now looked like a correct checksum. Would that cause the transfer to fail? Yes, it would. I think these are all probabilistic arguments that the probability that this happens is very low. And this is why people will worry about how many bits do you have in your checksum and what's the probability that a bit gets flipped. But this is like the extremely low probability worst case. If it happens, yes, even solution 2 would fail. And there have been a few cases where those things have happened and has led to endless debugging pain. Any other questions? Yep.
But don't we need the network to work so most of the time? So you have to be doing checks anyways in the network to make sure like the fixture. So
Yep. Hold that thought. So with that, okay, I hope the argument so far told us we had to implement reliability in the ENSO system. And you didn't have to do it in the network. But is there ever a case where you would want to implement reliability in the network in addition to implementing it at the end host? So we can't get away from having to build it at the end host. But is it ever a good idea to add it to the network? And you were getting at the answer there. Thoughts? Yeah? Right. So the answer is performance. Right? That sometimes having some amount of raising the level of reliability in the network is going to help even the end-to-end systems. So the simple example is if you think of having 10 links, and I say that each link can drop a packet with a 10% chance, then the chance of getting my packet across the network is really low. I have a 65%, don't bother with the math, but I have a 65% chance that that packet is going to get dropped. Instead, if I said every link is going to resend the packet twice, very simple reliability technique, my per link probability of an error drops really low, and my end-to-end reliability goes up really high, much higher. So it's much better. So in this case, you would say, the answer to the question is, yes, sometimes you do want to put reliability into the network. The reason we're doing it, though, is as a performance optimization, not for correctness. Okay. Even if I'd had a 65% chance of my network dropping packets, I would not have impacted the correctness of the end-to-end system. I'm just helping it perform better at this point. Right? And there's a lot of discussion on how do you evaluate whether it's a good idea to put in reliability for performance optimization and so on. This tends to be a case-by-case analysis that people will do. And so famously, I think wireless links are the ones that will do a little bit extra work to be more reliable. And so just to recap the end-to-end principle, what it tells us is that implementing a particular functionality in the context we've been talking about, that's reliability in the network, it doesn't reduce end-host complexity. You still have to implement reliability at the end host. You have to do that end-to-end check for correctness reasons. It does increase network complexity because you are now doing this additional mechanism that you're putting in the network for reliability. And whatever extra machinery you're putting in the network in order to make that link more reliable, that overhead is shared by all applications. Right? So you're sending a message, waiting for the ACK, resending the next one, and you're doing this at every link. That adds delay, for example. It adds state in the switches. And if you had an application that didn't care about reliability, it's still going to incur that overhead, whether you like it or not. And so, bottom line, you can add some functionality, reliability into the network, but it's more of a performance enhancement. And so this is the actual end-to-end argument in Clark's words. I'm not going to try and read it. I'm leaving it here on the slide so that you can read it offline. But it basically summarizes everything we've said so far, which is think about correctness, think about completeness, and most importantly, think about this end-to-end picture. This is tremendously useful even if you go out and on an internship or a job and you're asked to build a particular feature, understanding the end-to-end picture in which that feature operates is critical to helping you understand what capabilities need to go into the component you're building. And you'll find the end-to-end principle is referenced constantly when we talk about slightly more complicated distributed systems. And so with that, just to recap this portion of kind of the top-down view of how the internet works, the key parts you should remember on the how, which is how do you decompose a system into modules, Our answer was layering, and strict layering in particular. Where are these layers then implemented? We had this partitioning between end hosts and the network. And crucially, we had this one unifying protocol IP. That's what stitches together these different networks. On why did we do it that way? Layering, because it enabled an innovation by having a clean separation of concerns. And the end-to-end principle as a decision for what not to put into the network. Sometimes the functionality you don't add is actually more important than the functionality you do add. It kept the network simple and has allowed the internet to scale. With that, in the last minute, any questions? And we'll come back to the end-to-end principle with a more critical view of it at the end of the semester. Any questions? Yes. Right. Thank you. And I hope you all saw my post on, Sean's post rather, on Ed about the next 4 lectures and how we're going to run them in a slightly different style. I suspect this mostly impacts those of you in this room here, so we do want to make sure it's a good experience for you. We'll check back at the end of the experiment and see how it goes. Thank you.